Good day everyone and welcome to this presentation. My name is Aasen and the title of the presentation is Rig Assist Snubbing, Drillpipe Pressure Controlled in Managed Pressure Drilling and Underbalanced Drilling. Engineering contributions to be discussed for the two defined operational scenarios are equations for two buckling types in the snubbing rig, the use of effective force for all design calculations to include well pressure. What is snubbing and why use snubbing? Snubbing is the process of tripping pipe in a live well where the expulsion force created by the surface pressure is greater than the self-weight of the pipe. When running in hole with pipe, we need to push. When pulling out a hole with the pipe, we need to hold back. If we let go, the pipe will be ejected from the well. Shown in the picture is a standalone snubbing operation in the North Sea. Starting from bottom, we observe the pipe lying horizontally and rigged up vertically, the blowout preventers, work window, snubbing jack, work basket, and at the very top the mast and winch used for pipe handling. In rig-assisted snubbing, a snubbing jack is used together with a drilling rig. Shown in the picture is underbalanced drilling in the southern North Sea in the UK sector. The snubbing crew is in charge of tripping while pipe light, while the drilling crew operates while pipe heavy and while drilling. There is a dedicated snubbing blowout preventer stack that is located above the drilling BOPs. For the depicted offshore UBD operation, both the snubbing jack and the snubbing BOPs are located below the cantilever deck on the jack-up drilling rig. The expulsion force acting on the drill pipe is equal to surface pressure multiplied by the sealing cross-sectional area in the blowout preventer. Depicted on top is a set of ram blocks where the Teflon sealing element is seen in white. In ram-to-ram snubbing, we push the pipe body through the BOP while keeping the surface pressure below contained. Shown below is an annular BOP, which is designed to seal on an irregular surface, such as bottom hole assembly or pipe connection. The expulsion force is proportional to the square of the sealing diameter. For the field case discussed later in the presentation, we note that 4400 psi surface pressure creates an expulsion force of 78,000 pounds when snubbing the 4 3/4 inch bottom hole assembly, which is nearly twice that of snubbing the 3.5 inch pipe body. The basis for the presented well entry design is the maximum snub force. The design case happens when snubbing the first joint. Snub force is calculated by adding the expulsion force and the sliding friction force together. Since friction force works in a direction opposite the drill pipe movement, the snub force running in hole is higher than the snub force pulling out of hole for the same wellhead pressure. The purpose of the well-designed calculations in this paper is to verify drill pipe pressure control given the combined effects of compression, buckling, and pressure differential. The NORSOC D010 well integrity standard is mandatory on the Norwegian continental shelf. Depicted are the well barriers for tripping drill pipe in underbalanced well fluid. There is an underlying two-barrier philosophy. The primary well barriers shown in blue are for normal operation. The secondary well barrier envelope shown in red is the backup for failed primary barrier. The ultimate well control action is to cut the drill pipe and seal off the well bore using the shear seal ram. In this paper, we consider the contingency case of leaking check valves at the pipe bottom, which causes a blowout as well fluids escape to the atmosphere through the inside of the pipe. We consider a less dramatic contingency option instead of cutting the drill pipe, which is to deploy the safety valve at the top of the drill pipe. The normal operation is that we have check valves installed at pipe bottom that prevents the pressurized well fluid to escape to the atmosphere. In the drawing, this is shown as NRV no return valve. The entire expulsion force acts at the end of the drill pipe. Outside the well, above BOP, the effective force is compression and we face buckling issues. If the critical buckling limit is exceeded, we utilize a tubing guide to prevent the drill pipe to break. Inside the tubing guide, we allow buckling to take place and check for the combined effects of compression and buckling. Inside the well, below BOP, there is no buckling since the effective force is zero, but we need to check for the combined effects of collapse pressure and axial compression. In the contingency case, the check valves at bottom have failed and we have installed a safety valve on top to stop the blowout through the drill pipe. The expulsion force is split in two as we can see, but the total expulsion force is unchanged. Outside the well, we face buckling as before. In the contingency case, we now have pressure inside the drill pipe as an added feature. Inside the well, there is no buckling as before since the effective force is zero. In the contingency case, there is no pressure differential inside the well. The well design is therefore limited to compressive stress caused by the surface pressure acting on the pipe wall. The effective axial force concept is quite useful in well engineering. Not only is it equivalent to the buckling force and also represents buoyancy, but it is also the force to be used when calculating von Mises stress. The hydrostatic stresses are removed from the real axial force as shown in the equation. Remaining is a true representation of deviatoric stresses which causes yielding. For the effective axial force, we set neutral axial stress as datum, while for the real axial force, we use zero axial stress as datum. Unsupported buckling is shown below the traveling head on a snubbing rig. On top of the traveling head, the traveling snub slips grip the drill pipe and pushes the pipe into the well. If the critical buckling force is exceeded, the drill pipe will deflect laterally and finally break. This is a severe case of losing drill pipe pressure control. We consider design equations from both the steel structures industry and from the oil field. We also show results from unsupported buckling experiments in the university workshop. The chosen steel structures model for unsupported buckling is made up of two different formulas. For short compression members, we use the Johnson formula, while for long unsupported length, we deploy the Euler formula. Depicted is a dimensionless representation of these equations. At very short length, the buckling limit approaches the yield limit of the drill pipe. Equation 9 was introduced to the petroleum engineering literature in 1988 to calculate the slenderness ratio, which is a fundamental quantity used in unsupported buckling calculations. A great deal of effort has been spent trying to track the origins of this formula, but unfortunately without success. As discussed in the paper, it is found that the 1988 formula is of no practical value for calculations involving buckling of drill pipe and other jointed pipe used in snubbing. It is recommended to use equation 6 to calculate the slenderness ratio and disregard equation 9. Buckling experiments were conducted in the university workshop for several pipe sizes with 3.5 inch as the greatest outside diameter. All selected buckling lengths correspond to the Johnson parabolic formula discussed previously. Both ends of the pipe were free to rotate using a ball and seat arrangement as seen in the picture. Axial force and displacement were logged and also displayed on a computer screen. Two cameras were rigged up 90 degrees apart to film these experiments, showing both the shape of the pipe and recorded data. The Johnson formula was found to give a safe estimate of the critical buckling load. We consider helical buckling inside the tubing guide. The tubing guide is a fairly standard part of a snubbing rig, and it is designed to limit the amount of lateral deflection of the pipe after reaching the critical buckling limit. The pipe is allowed to buckle inside the tubing guide, and we assume that it becomes corkscrewed in the design equations. Helical buckling is not a problem as long as the total stresses remain below the yield limit of the drill pipe. If the pipe is compressed and buckled beyond yielding, we have drill pipe pressure control issues due to permanent change in shape. The pipe becomes permanently corkscrewed, and we no longer get a good pressure seal in the BOP. In the following, we introduce a dimensionless yield circle and define a concept that we call percentage yield radius. Real axial force and zero stress datum produces a triaxial ellipse, while effective force and neutral axial stress datum produces a triaxial circle. In this paper, we use the latter due to simplicity and agreement with buckling stability. For drill pipe and snubbing workstring, the diameter-to-thickness ratio is low, and collapse failure is modeled as a yield failure. We can therefore make the circle of plasticity dimensionless as shown. At radius equal to 1, the 1 Mises stress is equal to the yield strength of the pipe. Inside the circle we have stress below yielding, while outside the circle the drill pipe is yielded. The pipe can fail either on the inside pipe wall or on the outside pipe wall. According to theory, the pipe will never fail at other radial positions. The shown x-coordinate include both straight axial stress and bending stress due to helical buckling, while the y-coordinate represents the effect of the pressure differential. The percentage yield is a vector starting in the circle origin, and it is numerically equal to the inverse of the design factor. In triaxial design, we usually require design factor equal to 1.25, which is the same as 80% yield radius. The UBD field case is drilling a 6-inch reservoir section in a gas well. The formation is sensitive to drilling damage, and commercial production relies on avoiding killing the well once the reservoir is penetrated. The maximum snub force is 93,000 pounds while snubbing the bottom wall assembly, and 50,300 pounds while snubbing drill pipe ram to ram. The unsupported buckling calculations clearly demonstrate the need for tubing guide for this job. Triaxial calculations carried out for both normal operation and contingency case show maximum value of 65% yield radius, which corresponds to a design factor of about 1.5. This is a sound well design which ensures drill pipe pressure control. We have analyzed drill pipe pressure control for both normal operation and contingency case when snubbing drill pipe at maximum compression during live well entry. All needed design equations have been presented for both unsupported buckling and helical buckling. For unsupported buckling of drill pipe, the use of standard steel structures buckling formulas are recommended. An alternate definition of slenderness ratio introduced to the oil field in 1988 and later adopted by the snubbing industry is not recommended. Helical buckling is analyzed in the paper using a dimensionless yield circle. All needed equations are provided. This is a highly recommended method due to its simplicity and accuracy. Effect of pressure inside and outside the drill pipe is naturally taken care of by using effective axial force. A North Sea UBD field example is provided in the paper.